Hello everybody. We're going to have a look at this device you see on screen. It's called a Vernier Caliper and it's used in the graphical analysis lab activity that you'll be doing. And the idea is the Vernier Caliper will be used to measure the diameter of a variety of different steel ball bearings. Let's have a close look at that caliper, see how it works. I'll pick it up and point out this is a button. It's actually a brake. And before you can open or close the jaws of the caliper, you need to first push down that button and then pull back or push forward. If you don't push down on the button, the jaws are very hard to move, and in fact, you could possibly even damage the caliper. So when moving the jaw back and forth, make sure that you push the button down first and then slide it in whichever direction you decide you'd like to go. A lot of things change when we slide this piece of the Vernier Caliper. The part of the Vernier Caliper, though, that we're going to be most interested in is in the jaw section right here. Now, this region of the caliper here and here is a knife edge, and you will not be using the knife edge in this experiment. It's there, but it's meant for a different type of measurement that we don't need to worry about. Also, the recessed area here of the caliper is another part that we won't be using today. However, we will be using the region of the caliper right here, midway. And there we have a nice flat surface that we can push up against the ball bearing. So we are going to be using this section of the caliper, and that's where we'll be putting our ball bearing. To demonstrate, I've got a ball bearing here in my hand, and you open up the jaws as far as they need to go, hold the ball bearing, and gently close the jaws around the ball bearing just enough that the ball bearing doesn't slip out. Don't press hard, don't push with great force. The calipers could be damaged, and most certainly your measurement will be off. Just a gentle squeeze is all that's needed, and when you're done, remove the ball bearing and perform your measurement. Speaking of measurements, let's have a look at how measurements are made with an example. Okay, so I'll put the caliper in a position right now. Let's do something wildly different, shall we? And yeah, that'll do just fine. And we'll take a picture of that and then take apart the measurement that we've got there. Okay, so let me paste that so that we can look at it and figure out how to use the caliper to make this measurement. You'll notice that there are several scales, and when we perform our measurements, we're going to be using this scale right here, as well as the Vernier scale right down here. Okay, so we'll be using those two scales as we perform our measurements. These calipers measure in centimeters, and so the scale that has numbers on it, 0 centimeters, 2 centimeters, 3 centimeters, and so forth. Just a reminder that anything that we write down needs to be in centimeter units. Very good. Okay, with that in mind, what we do is we look for something that I like to call the pointer. And the pointer is this line right here. It's associated with the 0 on the Vernier scale that's highlighted in green. Okay, so once we find the pointer, we determine where that pointer belongs or is lined up on the centimeter scale above it. It's pretty clear that I got past 3 centimeters, but I didn't get past 4 centimeters. The position of the pointer is between 3 and 4, and that is the first thing that I'll use in determining my measurement. My measurement will acknowledge the fact that I got past the 3 centimeter mark, but never got past the 4 centimeter mark. Next, all of your Vernier measurements today must have 2 decimal digits. 1, 2. Okay? 2 decimal digits are required, and in fact, the uncertainty in all of our measurements will be plus or minus 0.01 centimeters. Okay, so as long as we can agree on the second decimal place, plus or minus 1 digit there, we'll all be in agreement. Now, as we look at the pointer again, returning to that and zooming in on it just a little bit more, let's add some marks just to make sure we all see where that pointer is. So 3 centimeters is clearly marked. We've got 3.1 centimeters, 3.2 centimeters, 3.3, 0.4. Let's go ahead and just put them all in. You know, we have 10 divisions in this space that separates the 3 and 4 centimeter mark. And so we can divide that up into tenths. Now we look at the vernier caliper again in the very same way. It's pretty clear that the pointer that I have here gets as far as 0.3, but never crosses over the 0.4 mark. So for that reason, I can write down the first decimal digit as the 0.3. So let's do that in a slightly different color. I've identified this as the next decimal digit. Okay? And I have my first decimal place. Getting the first decimal place is really just a matter of checking to see how far the pointer got, or more importantly, how far it didn't get, and then writing down the tenth. The second decimal place looks like it could be a bit of a guess. We're looking at this now, and we're trying to determine in the space between 0.3 and 0.4, right here, I guess green on green doesn't show up so well, but in that space, how far are we along? Mentally, trying to divide up that space into 10 pieces and coming up with an approximation would be a good way to proceed. However, the caliper has the vernier scale, which is quite useful in getting the second decimal place. The vernier scale that we used so far only for its pointer ability gives us actually the second decimal. Okay, and here's how you use it. Look across the vernier scale. Let me demonstrate. Here is the line for 1. Notice how the line on the vernier scale for 1 does not line up with any of the tenths units in the centimeter scale. No good. Let's go on to the 2. Nothing lines up. On to the 3. Nothing lines up. Well, will we ever get to a point where the lines line up? And it looks like this is it. Here we see alignment. And that's what we want to see. When we see that the lines line up like this, we take the number from the vernier scale and we put it into the second decimal place. So this measurement then would be 3.38 centimeters plus or minus 0.01. Let's try one more example just to see how this works, and then you'll be able to practice a little bit also with the lab handout. So let's go back to the camera, have a look at a slightly different measurement. One more measurement just to practice our skills a little bit. There it is. We'll take a picture and then really zoom in on it to see if we can't determine the measurement and what it should be. Okay, so here we go. And let's have a look at the centimeters first. Okay, so here I have 5 centimeters, 6 centimeters, and 7 centimeters. And as I look at the pointer, which is right here, I do pass by the 6 centimeter mark, but I never get as far up as 7 centimeters. So what this is telling me is that my first part, the first part of my measurement, is going to be 7, try that again, 6, centimeters, but don't forget, we have to have 2 decimal places as part of that. So 6 centimeters for sure, certainly not 7, not nearly that big. The next thing that we do is we take an even closer look at the decimal part of this. Here is my 0.1 mark and my 0.2 mark. I don't need to go very far because it's pretty clear that the pointer falls within the range from 0 to 0.1. And so, since we never pass the 0.1, we cannot claim it as the first decimal digit, and instead we'll have to write a 0 right here. But the truth is, the pointer did go a little bit further than 6. And that little distance further than 6, although it may not have been a tenth, and we may not be able to write it as a 1, we will be able to refer to that distance in the second decimal digit. Recall, to do this, we look at the Vernier scale, and we look for alignment. So let's do that. Here is 1 on the Vernier scale. It doesn't line up. Here is 2 on the Vernier scale. It doesn't line up. 3 is really getting close, but I think that 4 is probably the best. 5 is off the mark. 6 is off the mark. To me, it looks like the number 4 on the Vernier scale needs to be the second decimal place. And so we take that and we write it here, and we include plus or minus 0.01 centimeters as our measurement. This one demonstrates how we can have zeros as decimal digits. Just remember that all Vernier distance measurements are in centimeters, and all must have 2 decimal digits. Well, that's it. Practice those problems on the lab handout, and we'll see you in lab.